So thank you for the introduction. I'm very honored to be here to give a talk. And today I'm going to talk about our recent progress on asynchronous MPC. So you can see, as the title says, that we actually achieve a linear communication for the asynchronous citing. And this is a joint work with Vipo Goya, Chenda Liu Zhang, and Xiaoyu Ji and Jie Li. Okay, so we just follow the standard model that there are n parties and T of them can be corrupted. And we also assume there is a point-to-point communication channel between every pair of parties so that they can just send messages between each other. Okay, and we want to make sure that eventually all the parties, all the honest parties should obtain their correct results. And we also want to make sure that adversary does not learn anything beyond what he can learn, which is just the function output and his own input. So there are several different models in MPC, and for the most two common models considered in network are the synchronous citing and the asynchronous citing. Basically, whether you assume there is a fixed time bound for every message. So for the asynchronous citing, every message can be arbitrarily delayed, and the delay is not known. So usually we just assume the delay is controlled by the adversary. And for the adversary, we can consider semi-on security and also the malicious security. And for the computation power of the adversary, if you consider the computational citing, then you can use some cryptographic tools, or you can assume that the adversary is not bounded, which corresponds to the information serial security. So in this work, we consider the asynchronous citing for malicious adversary and information serial security. So before introducing our results, I want to briefly mention the difference between the synchronous citing and the asynchronous citing. So in the synchronous citing, there's a fixed time bound, so that, let's say if a party A sends a message to all the parties, then a party B should learn this message after this bound T. This also means that if this party B does not receive this message, then it must be the case that A is corrupted and does not send this message to B. So B can just set this message to be some empty symbol and proceed. So we know that in this case, for information theoretic security, it is possible to achieve malicious security with N/2 corruption if you assume broadcast channel. But in the asynchronous citing, the case is that there's a delay for every message, and this delay is not known. So if you do not receive a message, we don't really know whether this is because that the adversary, the party A is corrupted and does not send the message, or it is because that this message is being delayed by the adversary. So you can only choose to wait, but if we want to achieve liveness, meaning that you should not, the protocol should not stop just because the corrupt parties. So we want to proceed. So due to this difficulty, in the asynchronous citing, the best possible corruption threshold we can achieve is N/3, even for the computational citing. Okay, so in the synchronous citing, the best the early feasibility result is established by the well-known result BGW protocol, and in d1s4-1, Damgard and Nelson proposed the first linear communication MPC against N/2 corruptions and with semi-on security. And later on, the work by Bensensen, Fer, and Ostrowski shows that you can also achieve malicious security with linear communication. On the other hand, in the asynchronous citing, the best known result we know requires n⁴ times the circuit size. Okay, so you can see there's a large gap between what we know for the synchronous citing and what we know for the asynchronous citing. So this leads to our main question, whether we can construct asynchronous MPC with N/3 corruption that achieves linear communication in the number of parties. So our result shows that if you have a large field, so basically we require the field size to be 2 to the power of the security parameter, and then it is possible to achieve a linear communication. But I want to mention two limitations. So you can see that first, our work only works for the large field. This is because we have a soundness error, sorry, not soundness error, but statistical error that is negligible in the security parameter. And or we require the, okay, so this is because the error is proportional to the inverse of the field size. So it will be interesting to see whether we can maybe mitigate this limitation, because for the synchronous settings, there are several different techniques that allow you to construct MPC over small fields or even over the binary field. And the second limitation is that you can see we actually have a very large overhead in the number of parties. So there's term of n to the power 14. So it's definitely not practical. And this is somehow due to the tools we are using, but we hope that future works can improve this factor. Okay. And also a relevant mention is that it's also very interesting whether we can achieve linear communication for perfect security in the asynchronous setting. And this is actually known in Eurocrypt this year. And actually, Professor Patra will introduce their result later. Okay, so let's start from the general approach of constructing MPC. So basically, we rely on the secret sharing scheme, and we let each party share their input in the beginning, and then we try to compute a secret sharing for every value in the circuit. And once you obtain secret sharing for the output, then you can reconstruct the result. And here we follow the previous work to use the Shamir secret sharing. Basically, we use a random polynomial to hide the secret at point 0, and each party has its share as one evaluation of this polynomial. So we use a degree T polynomial so that if you only have T shares, which are not sufficient to determine the polynomial, so you don't learn the secret. But if you have T plus 1 shares, you can interpolate the whole polynomial and determine the secret. And we are going to use two properties of the Shamir secret sharing. The first one is linear homomorphism, so you can compute addition gates or linear operations. And the second one is error correction. This is inherited from the Reed-Solomon code of the underlying secret sharing scheme. So in particular, if you have just one third corruption, then you can reconstruct the secret sharing even if T out of them are incorrect. So that means that quiet parties cannot stop honest parties from reconstructing the secret. And in particular, this also works in the asynchronous setting. Okay, now for addition gates, we can just use the linear homomorphism of Shamir. We don't need to do any interaction. But for multiplication gates, we want to compute from sharings of x and y to sharing of their multiplication. And here we choose to use Beer triples. The reason is that the Beer triple allows us to reduce the task of multiplication to 2 reconstructions. And we just mentioned that quiet party cannot stop honest parties from doing reconstruction. So in this way, we can ensure that the online phase or the computation of the circuit will never fail. And actually, from previous work, we can already achieve linear communication, assume that you have enough Beer triples. That means that if we want to achieve linear communication, the only thing we need to do is to prepare Beer triples. Okay, so usually this is further divided into 2 parts. The first part is called asynchronous complete secret sharing. So basically, we want a dealer to share degree T Shamir sharings to all the parties so that all the honest parties should eventually obtain their shares. And with this tool, we will let all the parties to generate the random Beer triples. So the previously best known result is due to Trotwood and Petrie in 2023 for ACSS, which requires n-cube communication per sharing. And for generating Beer triples is the work from CP17 that requires n-square communication plus sharing out of n degree T Shamir sharing via ACSS. And if you compare the result we know for the synchronous setting, then there's actually a n-square overhead for the first step and out of n overhead for the second step. So this means that if you combine these 2 parts together, you will have n-cube overhead compared with the best known result in the synchronous setting. And in this talk, we are going to solve both of these questions. So we will achieve just out of n communication per sharing, and to generate Beer triple, we only require out of n communication plus sharing a constant number of degree T Shamir. Okay, so let's start from the first part about constructing ACSS. So I want to first talk about the difficulty, like why this question is difficult. So imagine that now the data is corrupted. So the data want to share sharing to other parties. So because we assume that the adversary is fully malicious, which means that the adversary can choose to send incorrect shares to honest parties or just to choose not send anything. But recall that the guarantee of the ACS is that all the honest parties should eventually obtain their shares. So let's just consider two honest parties. The first honest party, P1, which has a very good network, so he will quickly accept his shares. Let's say after some time bound top. But on the other hand, say the second honest party, P2, has a very bad network, so his network delay is even larger than tau, which means that at the moment that P1 accepts his shares, P2 does not receive anything. But because the guarantee of ACSS, we need to ensure that P2 should eventually obtain his shares. But due to this delay, we cannot rely on any response from P2. So in the worst case, we can only hope that T+1 honest parties obtain their shares when they accept, when they think that the sharing procedure succeeds. And we need to rely on these T+1 honest parties to recover the shares of the rest of T honest parties. A weaker goal is called asynchronous verifiable secret sharing. So this secret sharing scheme only ensures that once the sharing procedure succeeds, then you can always reconstruct the secret. But it does not guarantee that all the parties will obtain their shares. So the previous work constructs ACSS by first constructing an AVSS that has quadratic communication. And then they show how to upgrade from AVSS to ACSS by using an instance of AVSS. So let's try to get some intuition why this works, and let's see how our technique can be applied. So the idea is that we try to sharing not just degree T polynomial, but a degree T bivariate polynomial. So we have a degree T, we have degree T for both variables. So you can think that this is just the extension of the Shamir secret sharing. And now each party should obtain one column and one row, which are just two degree T polynomials. And we store the secret at point 0, 0. So in the first step, the dealer will send column polynomials to all the parties. And let's now, just for simplicity, assume that there is a signature scheme. Of course, in the information serial setting, we don't really have signature scheme, but let's just assume this one. So in the beginning, the dealer sends column polynomials to all the parties, and he will, once the party receives his column polynomial, he will sign his column polynomial and send the signatures back to the dealer. And now the dealer's job is to wait for 2T+1 parties signing their column polynomials. And we can see that because we only have T quiet parties, so at least T+1 honest parties has already signed their column polynomials. And we can say that the bivariate polynomial F is determined by the column polynomials of honest parties who provide their signatures. And now for the second step, the dealer will distribute row polynomials together with the signatures he received from the previous 2T+1 parties. And now each party only accepts his row polynomial if he received all the correct signatures. Now the guarantee is that if a row polynomial is accepted by some honest party, then we claim that this one must lie on the bivariate polynomial determined by honest parties. The reason is that due to the signature for this degree T polynomial of each row, it has already agreed on T+1 points because T+1 points are provided by honest parties. Okay, so once 2T+1 parties accept their row polynomials, then we think the sharing procedure succeeds. So how should we reconstruct the secret? We just need to send row polynomials and also with the signatures. And now we can rely on the row polynomials with correct signatures to do the interpolation. And because we know T+1 honest parties will obtain their row polynomials, so you can expect T+1 correct row polynomials. And this will be sufficient for you to interpolate F and recover the secret. Okay. So, of course, there are some issues we omitted. For example, we don't really have the signature scheme, so we actually need to use the so-called asynchronous information checking protocol. And also, unlike the standard signature scheme, ASAP is not transferable, meaning that if you receive the signature from, say, the dealer, you cannot actually use this signature to convince another guy that this message is from the dealer. So this requires some other techniques. But even omitting all these issues, you can see that the communication per sharing is out of n squared because you need to, the dealer needs to send row polynomials and column polynomials to every party. Okay, so a natural solution of reducing this factor of n is to try to use packing. Like say, we try to use a larger degree Barrel polynomial so that we can store more secrets. So let's say we use a degree t 2t Barrel polynomial. So now each row still remains degree t, but each column becomes a degree 2t polynomial. And in this way, we can store multiple secrets. So let's see, try to just use the previous approach and see where this the same approach breaks. So following the previous approach, we still let the dealer to share the column polynomials in the beginning and wait for signatures from 2t plus 1 parties. And following the same argument, we know that ith parties so at least the t plus 1 ith parties will provide their signatures, and from those t plus 1 ith parties, we can determine the polynomial f. And the second step is to distribute the row polynomials with signatures, and we can also argue that the row polynomial accepted by ith parties are also correct. But the issue is that when we try to do the reconstruction, so in the previous approach, we let each party provide their row polynomial with signatures. And we can use the row polynomials of ith parties to recover f. However, here we have a larger degree, and if you want to use row polynomial to determine f, you actually need 2t plus 1 polynomials. But unfortunately, we can only have t plus 1 of them. So this is the actual issue. However, if we go back to step 1, we have just explained that after step 1, from the t plus 1 honest parties in this set M, their column polynomials can already determine the Barrel polynomial f. So the question is that, can we just use the column polynomials of ith parties in M to reconstruct f? So the problem is that, although we can expect ith parties provide their correct column polynomials, but correct parties may provide the wrong column polynomials. And in case that you only receive t plus 1 correct column polynomials, but t incorrect column polynomials, you don't know which one is correct or wrong. And this causes the trouble of reconstructing f. So we will use the authentication tag introduced by Ben-Sanson, Fair, and Ostrowski, where this technique is actually used to build linear communication MPC in the synchronous setting. So the idea is that for two parties, P and PB, if PA wants to authenticate his message M, PB will first choose two authentication keys. So the first one is a long-term key, mu, which has the same length as the message. And the second key is nu, is a short-term key that is only a single field element. And the tag is computed by the inner product between M and mu plus nu. So in this way, we will let the PA learn the tag, and later PA will send message M together with the tag so that PB can verify the message. And I want to mention that the long-term key can be actually used to authenticate multiple messages, and only the short-term key needs to be refreshed each time. So our idea is that in the beginning, during the sharing phase, we will let all the parties in M, so for every party PJ in M and for every other party, we will let the party PI in M and PJ to be any arbitrary party. We want PI to authenticate his column polynomial to PJ. Of course, it's not known how to do this for now, but let's just say now suppose we have the text. So during the reconstruction, we'll let each party just provide their column polynomials together with the tag. Now, because of the tag, now the receiver can distinguish from the correct polynomials and the wrong polynomials. So we will only use the correct polynomials to do the interpolation. Actually, authentication tag is much more useful than just doing the reconstruction. So we can upgrade from AVSS, which only ensures reconstruction, to ACSS, which ensures that all ANS parties can obtain their shares. So the issue of AVSS is that when we do the reconstruction, we actually reconstruct the whole polynomial. So you actually know every party's shares. But if you want to achieve ACSS, we just want you to learn the shares you should learn. So let's say now we try to first reconstruct the row polynomial to every party. So we ask parties EM to send only the points that PJ should learn. And now PJ can obtain T+1 correct shares from ANS parties, but he can also obtain T incorrect shares from correct parties. So again, we face the issue that we need to distinguish the correct shares from incorrect shares. But this time we cannot rely on the tag because the tag is for the whole column polynomial. If you only have a partial information, you cannot check the tag. But the point is that authentication tag is linearly homomorphic. So we can actually ask all the parties to open a random linear combination of all the barrier polynomials, so that in this way, you can check whether the share you received from, say, the party PI is correct or not. Okay? So this means that PJ will receive shares from different parties, and each time he receives shares from PI, he will ask all the parties to reconstruct a random linear combination of all the polynomials and check whether PI's shares match this polynomial. And of course, due to the privacy, each time we actually need to sacrifice one random barrier polynomial. So the guarantee is that now every ANS party should eventually obtain their row polynomial. Now we move to reconstruct the column polynomial. We just do the same thing. So this time, we'll let every party, after obtaining their row polynomial, send only the points PJ should learn to PJ. And because we just argued that every ANS party should obtain their row polynomial, so we can hope we can receive 2t+1 points, which are sufficient to interpolate the column polynomial. But again, you need to distinguish from the correct shares and the wrong shares. We just use the same trick. Each time you receive the shares from PI, you check a random linear combination, and you let all the parties to open this one. Okay, so in this way, we can upgrade from AVSS to ACSS, such that the communication cost, the additional communication cost is just sublinear. Now the remaining question is to compute the authentication tag. So the first issue is that to make our ideal work, we need PI to authenticate his column polynomial to every other party. But as I mentioned, in the asynchronous setting, you cannot hope every party responds. So we are going to prepare the authentication keys in a disputed way. We are going to use ACSS to prepare authentication key. So the good news is that the authentication key is sublinear in the total message you want to authenticate because long-term key can be reused. So we can just use some ACSS construction from the previous work, although they don't have linear communication, but that is fine. And now, the observation is that the values we want to authenticate has already been T-shared. So let's say for the first party P1, we want to authenticate P1's column polynomial. But every point in his column polynomial is also in a row polynomial, which is a degree T polynomial. So this means that every value we want to authenticate has already been T-shared, except that now the secret is not stored at position 0, but at position alpha 1. By the way, so this is just observation in the BFO 12. So with T-shared of both the keys and also the column polynomials you want to authenticate, all the parties can compute a degree 2 T sharing of the authentication tag. So here, for simplicity, we omit the issue that if you don't re-randomize this degree 2D sharing, then there may be some information leaking. Okay, so to let PI obtain the authentication tag, all the parties will send their tag share to PI. But because this is a degree 2D sharing, so again, we need to distinguish from correct shares and wrong shares. And this time we don't have authentication tag. How should we do that? So the point is that the dealer can actually help all the parties reconstruct the barrier polynomial. So remember that this is a sharing phase. So the dealer needs to be online to make this sharing phase succeed. So the dealer can just broadcast polynomial f together with the signatures received from the original 2D plus 1 parties. So if all the signatures are correct, then we know that this one is correct. So with f, which means that you know the column polynomial is clear, then if you follow this equation, you can actually compute a degree T sharing of the tag share of Pj. So we just mentioned that degree T sharing can always be reconstructed. So in this way, the party Pi can verify whether Pj's share is correct. But this one will reveal f to all the parties. So how do we do that? Check a random linear combination. So, of course, this requires that the dealer needs to be able to open a random linear combination. And this is the place we extend ASAP, which is, just recall that this is used for the signature. We extend that so that the dealer can actually open some linear combination of his polynomials. Okay, so for a quick summary, so during the sharing phase, our goal is to let every party Pi and every party Pj so that Pi will authenticate his column polynomial. And the first idea is that we know that D can actually help all the parties do the reconstruction. And also we know that every party's column polynomial has already been T-shared by each row. So this allows all the parties to compute a degree 2D sharing of the tag. But to reconstruct the tag, you need to distinguish from the correct shares and the wrong shares. And this time, we need the dealer to open a random linear combination of all the barrier polynomials so that you can compute a degree T sharing of each party's share so that you can verify whether this party gives you the correct share or not. And now, once you have the authentication tag, to let all the honest parties obtain their shares, so we only send the shares that this party should learn. And again, we need the party to distinguish the correct shares from wrong shares, and this is done by doing a linear combination. And this time, the reconstruction can be done using the tag. Okay. So basically, you can see we just reuse the same technique many, many times. And for the second part about triple generation, we want to generating random Beer triples. Any question? Okay, so usually this is done by first preparing the first two sharings, which are just the random degree T sharings. You can use ACSS. And for the second part, you need to multiply these two sharings together. And in the synchronous setting, usually we just multiply these two sharings directly so that you obtain a degree 2D sharing. And then later you need to reduce degree to degree T. And to this end, we need two techniques. The first one is double sharing, which are two sharings of the same random value R, but one has degree T and the other one has degree 2T. And the second one is party elimination framework. Basically, the degree reduction step can be easily go wrong. So you need to figure out which party does not follow the protocol. However, in the asynchronous setting, it's not very clear how to prepare double sharings efficiently. As we just seen that just preparing degree T sharings is already very difficult. And the second part is that usually to figure out who is cheating, you just let all the parties broadcast their views so that you can figure out which party does not follow the protocol. But the point is that in the asynchronous setting, you cannot hope all the parties cooperate. So it's not clear to how to find the party who is cheating. So in the previous work, Chaudhary and Patrick introduced techniques that you actually don't need to increase degree. So you don't need to reduce degree, and you don't need to face the issue of degree 2D sharing. And because degree T sharing can always be reconstructed, this can ensure that the generation process will always succeed. So the idea is that all the parties will first prepare 3 polynomials which are shared by all the parties. And in particular, the polynomial h should satisfy that h is equal to f times g. And now if you take any evaluation point, you can see that, say the point beta, then f beta, g beta, and h beta is just a Beer triple. Okay. Of course, we cannot hope all the parties participate, so let's assume that now we have 2 L plus 1 parties participate. So for now, you can just think that L is equal to T. I'm using L here is just for generality. Okay. Now, the point is that we'll let all the parties first just generating random Beer triples and share them. We can use ACSS for that. Then to build these 3 polynomials, we'll use the Beer triples from the first L plus 1 parties. We will use them as the evaluation points for the first L plus 1 points. And we set f and g to be just degree L polynomial. So in this way, h should be a degree 2D degree 2L polynomial. Okay, now because we have L plus 1 points for f and g, we can actually interpolate these 2 polynomials. So we can compute the evaluation result as the rest of L plus 1 points, the rest of L points. But we still don't have the missing L points to determine the polynomial h. And this is to use the Beer triple generated by the rest of L parties, and we just use the Beer triple technique to compute multiplications. Okay, so you can see in this way, we don't need to increase the degree, and everything, and the generation process will never fail. So if you want to obtain random Beer triples, you can observe that the tripartites can actually learn T rows. Either this row is using some Beer triple generated by this tripartite directly, or this row is computed by using the Beer triple generated from this tripartite. And because f and g are degree L polynomials, so there are L plus 1 unknown points, but T of them may be learned by tripartites. So this means that we can only hope to extract L plus 1 minus T random Beer triples. So you just can evaluate f, g, and h as this many of different evaluation points. However, we just mentioned that in the asynchronous setting, you can only hope 2D plus 1 parties participate, which means that you can only extract 1 Beer triple. So the amortized communication per triple will become n squared. Okay, now how do we shape this factor of n? Again, we want to we try to use maybe either pack secret sharing or some other ideas. And here we actually give 2 potential ideas. The first one is that you can use a larger L. We just mentioned that you can extract L plus 1 mass T Beer triples. But if L plus 1 mass T is out of n, then the amortized cost becomes linear. However, the issue is that now you need 2 L plus 1 parties participate, but this is not possible in the asynchronous setting. So this means that the whole process may never terminate. Or in other words, this process may fail because maybe there are not sufficient number of parties participating in the protocol. On the other hand, we can try to use packing. So let's say we try to pack multiple secrets within one sharing. So although this time we still only get 1 Beer triple, but this one is a packed Beer triple. So it stores multiple secrets. And if the number of secrets is out of n, then maybe later on we can depack them to be out of n standard Beer triples. So still, it's possible that this may give us a linear communication construction. But now the question is that when you use packed secret sharing, you actually need to increase the degree of the polynomial. And this means that we cannot rely on the error correction. So the process may fail due to some errors. And also it's not know how to prepare this pack sharing efficiently. So in summary, we can see that for the second process, the issue is that we may receive too many incorrect shares from tripartites. Or in other words, there might be too many tripartites participating in the second process. Okay, Now, I believe you have already observed that these two failure reasons are somehow contradictory, right? So for the first process, we want many quadriparties to participate so that you can have many Biot triples. And for the second process, we want not many quadriparties to participate so that we can use error correction. So our idea is that we want to unite these two processes so that if one party participates in the first process, then he should also participate in the second process, or the other way around. If a party does not participate in the first process, then he should not be able to participate in the second process. If we can do that, then we can see that either for the first process, we will have enough number of parties participate, so the first process will succeed. Or we will not have that many quadriparties participate in the second process, so that the second process will eventually proceed. Okay. And the idea of unite these two processes is actually very simple. So observe that in the first process, we just need each party to share their Biot triples. So a party participates in the first process just means that this party is sharing his triples. So in the second process, we require that a party Pj accepts messages from Pi only if Pj has already finished the ACSS protocol led by Pi in the first process. Now you can see if the party Pi does not participate in the first process, then no ith party will accept his message in the second process. And this is equivalent to that in the second process, Pi does not participate. Okay, so now our concrete goal is that for the first process, we want to ensure that if we have enough number of parties participate, then it should succeed. So we give the requirement here, if 2 plus epsilon times t plus 1 parties, or epsilon t quadriparties participate, then the first process should succeed. So I want to mention that because we know all the nth parties will participate. So if we have epsilon t quadriparties participate, then this means that there will be sufficient number of parties. On the other hand, if this requirement is not met, then we don't want parties to take incorrect or insecure triples. So we just use the previous approach, except that now we try to wait for more parties that share the triples. So you can see the first requirement is satisfied. And for the second requirement, if it not have many parties participate, then the first process will just not terminate. So parties will always wait for the first process. But it is fine because in this case, we can hope that the second process will finish. Okay, for the second process, it will a little bit involved. So we will consider the counterpart of the condition. That is, if there are at most 2 plus epsilon times t plus 1 parties, and at most epsilon t quadriparties participate, then the second process should succeed. So here we not only require that the total number of parties should not be too much, but also that the number of quadriparties should not be too much. On the other hand, again, if this requirement is not met, then parties should not accept incorrect or insecure triples. So our idea is that, recall that for the second idea, we try to use packing. So we'll let all the parties share packed Biot triples. We use degree d here. So d will be 1 plus epsilon times t minus 1, so that you can store epsilon t secrets in a single sharing. And then we follow the standard technique of CP17 to extract packed Biot triple. Of course, here we may need to extend the Biot triple technique to the packed Biot triple technique. And finally, we depack the packed Biot triple we obtain to the standard Biot triple. Okay, so let's just have a very quick look because I probably will not have enough time. So to secret share packed semi-secret sharing, so we just following the standard technique. But remember that in this case, we don't have that many quadriparties, okay? So we just let the data distribute both the row polynomial and the column polynomial to all the parties. And now there are two cases. Either you just receive the shares from the dealer, and then you are happy, you will support the dealer. And in the meantime, you will send the common point to the party PJ. Just try to help other parties recover their polynomials. So in the second case, you don't receive the shares from the dealer in time, so you probably will receive sufficient number of shares from other parties. And in this case, you can again interpolate your polynomials. And here we require 2 mass epsilon times t plus 1, just because some parties may not send share to you, even if they has broadcast that they support the dealer. And the sharing phase succeeds if we have 2t plus 1 parties receive their shares. But the issue is that, okay, so the good news is that because we only have a small number of parties, so you can expect that all the honest parties will obtain their shares. But the point is that there's no guarantee about the correctness. So either that even the dealer is honest, you may not obtain your correct polynomial just because the correct parties may send you incorrect shares. But the good news is that we only have a very small number of correct parties, so you can use error correction here. So we'll let parties to error correct their polynomials. So this makes sure that if the dealer is honest, then all the honest parties will obtain correct shares. But if the dealer is corrupted, then there's still no guarantee. So we'll run some verification protocol to check whether the sharing distributed by the dealer is correct or not. So I want to mention that usually this kind of check is not very useful because in the asynchronous setting, you need to proceed as long as 2t plus 1 parties response. And this means that when you generate the challenge, it's possible that t-honest parties have not received their shares. And once the adversary learns the challenge, he can just produce the shares of the rest of t-honest parties so that although the check passes, but their shares are still incorrect. But here, again, because we don't have that many correct parties, so we can expect that when we generate the challenge, most of the honest parties have already obtained their shares. And therefore, we can ensure that after the check, most of the honest parties will have the correct shares. Okay, so let me just skip the analysis here. I just want to mention that because most of honest parties will obtain their correct shares, so this is actually an AVSS, because once you receive 2t plus 1 shares, most of them are from honest parties, so you can still use error correction. Okay, now to upgrade to ACSS, where we want to ensure all the parties obtain correct shares, we just let the dealer to share each party's share by using the previous approach. And then we do some verification over all the share range distributed by D to check whether those shares lie on a degree D package secret share. Okay, so this way we can ensure that all the honest parties can obtain their correct shares. So by the way, here we can do this because we are using pack secret sharing. So even we share each party's share, this will not make the communication quadratic. And then we follow the trick of CP17 to extract a single pack bureau triple. And finally, we want to depack a pack bureau triple to standard Shamir secret sharing. And this can be done by just using some preprocessing data and following some standard trick. And here we just use the previous observation that you can prepare this kind of random data by only preparing degree T Shamir secret sharing. And this can be done by using ACSS protocol again. So let me just skip this part. So it's not very, I mean, you can check our paper, it's not very difficult. Okay, but we're not done yet because we just mentioned that it is possible that the success requirement is not met, and we are not able to verify whether this is the case or not. So we want to make sure that even if the success requirement is not met, parties should not accept incorrect or insecure triple. But they can choose to, maybe they can abort in this case because in this case, we can expect that the first process will succeed. So the bad news is that if the success requirement is not met, then all the guarantees we have discussed are gone. That means that honest parties may not obtain their shares, the error correction no longer works, and the final triple can be incorrect. But good news is that we can prove that if finally they finish the second process, then their bureau triple will contain some error, but the error will be restricted to the following form. So the adversary can add some additive error, epsilon1, epsilon2, epsilon3 on each of these sharing. And he can also choose delta 1, delta 2 to make the seed to be added with delta 1 times A plus delta 2 times B. So this is the only thing that the adversary can do. And in particular, the adversary does not learn any information about A, B, and C. So you can see that if this error satisfies certain requirements, then this will always be the correct triple. And in this case, we can call this attack a benign attack, because in this case, it's still a random bureau triple. We can ignore the attack. On the other hand, if this relation does not satisfy, then when we randomly sample A, B, and C, then with very high probability, this will not be a correct triple. So the only thing we need to do here is just to check whether all the parties have obtained correct triples or not. So we will do some verification protocol for all the triples. Okay, so this will be the final process. For the second process, we just add a final verification protocol. So in summary, the main observation is that we can design two different processes that can potentially achieve linear communication, but one may require many correct parties participate, the other one requires few correct parties participate. So our idea is that we can unite these two processes by requiring that a party can only participate in the second process if he has already participated in the first process. And the outcome is that now at least one of these two processes will succeed. And for the second process, so for the first process, we just follow the previous approach, except that we wait for more successful dealers. And for the second process, we can use error correction to let all the parties secret share degree T package area secret sharing. Then we use the previous approach to extract bureau triple, and then we depack. And finally, we add a verification protocol to ensure that all the parties can even obtain correct triples, or they can detect it. Okay, so that's all for my talk. Thank you.